Wait. My my name is Andrew Fritz. I'm a faculty scientist in the Stein Lab. And if you could hold your questions till the end and use the little hand raise symbol so that I can pick who the order of questions, that would be great. Thank you so much. So today's speaker is Josh Bongard. He's the Why Not Professor of Computer Science at the University of Vermont. His lab creates AI, robots, and computer-designed organisms. He received a research award from Barack Obama at the ceremony at the White House. Was named one of MIT's technologies.
It's AI at UVM, healthcare.
Sorry, if you could mute your microphones, thank you. He received a research award from Barack Obama at the ceremony at the White House, was named one of MIT Research Technology Review's top 35 under 35, and received the Cozzarelli Prize from the National Academy of Sciences. He has appeared on CNN, and his work has been covered by the New York Times, the New Yorker, and the BBC. He is also the author of the book, How the Body Shapes the Way We Think. So with that, I'd like to introduce Dr. Josh Bongard.
Thank you very much, and thanks to all of you for coming, and thanks to Gary for the invitation to come and speak today, and thanks to Sheila for pulling us all together. So again, thanks for the introduction. I'm Josh, a faculty member over here in computer science. I'm going to talk I'd like to talk today about AI not as a single thing, but as a collection of things. Medicine is not one thing, it is a collection of different things that has a particular approach to human problems. Same goes for AI. What I thought I would do today is actually delve into AI a little bit to give you a sense of how it actually works and how it's being applied in various ways in the clinical sciences. I am not a clinician. I am an AI expert now with the AI revolution. Everybody's an AI expert these days. For better, for worse, I've been working in the space of AI and robotics for about 25 years. It is my personal opinion that in this new age of AI, we all need to understand a little bit about what's going on under the hood. AI can be very scary to some folks. It can seem mysterious. It can seem magical. We are in the process of trying to legislate, legalize, somehow constrain this new technology. And it's very, very important that we all try and understand a little bit about what's going on. So if you'll forgive me, I'm going to spend the first 5 or 10 minutes taking you under the hood to show you a little bit about how AI works. And then we'll pull back a little bit and talk about current and future applications to various kinds of clinical applications and health outcomes. Again, that being said, I'm not a clinician, so I might speak a little bit out of school here. I will try and restrict my lecture here to AI. If you do have questions, I'll leave plenty of time for you to ask them at the end. So this talk is broken down into 3 parts. I'm going to talk about AI that is able to make predictions about health outcomes. Then I will talk about AI that can discuss in plain English about health outcomes. And then finally, I will talk about how AI can directly intervene in health outcomes. And it's this last part, intervention, that most of my lab focuses on, but we'll get there. Okay, so how does an AI make a prediction, and why does that matter for the clinical sciences? So I'm going to walk you through sort of visually how an AI works. There will be no math. Gary was asking about a final exam. No final exam here. I will skip over the math, but I'm going to try and take you down a little bit into the engine room of an AI. I'm going to start with a hypothetical example. Let's imagine, let me back up for a moment. AI is not magical. It's not something new under the sun. Ultimately, an AI, singular, is a computer program. It's a computer program running in a computer somewhere, either on your laptop or in the cloud or on your phone. It's a computer program. So imagine we want to train or teach this computer program, this AI, to predict whether a given image that we present to it is either a cat or a dog. In my slide deck, I use cats and dogs. For this audience, imagine that we present to the AI photographs of benign and malignant tumors. We know which are the malignant tumors and which are the benign tumors. The AI does not know. At the beginning, the only thing it knows when we present it with a photograph or an image is that that image contains a bunch of colors. So let's take this image of a cat. It's basically made up of a whole bunch of pixels, a whole bunch of colors. So I've got this little icon of an eye here. There's one part of an AI that takes as input colors from the photograph and turns those colors into numbers. Some of you may be old enough to remember paint by numbers. You have a blank sheet of paper with numbers on it. Wherever there's the number 3, you put some red. Wherever there's a number 2, you put some green. This is the opposite. The webcam on your computer and on your phone, it's
Josh, we're not seeing anything.
You're not seeing anything. Do people not see a picture of a cat on my screen?
I see
I
it.
see it.
Okay. I'm sorry, whoever asked that question, it seems the problem is on your side. You should be seeing a picture of a cat. Okay, I will carry on. So we have this picture of a cat, and the camera of the computer is pulling out the colors and turning them into a whole bunch of numbers that represent those colors. The first thing an AI does before it learns anything is it randomly compresses those numbers into a smaller set of numbers. So this little solid arrow that you see that takes this sheet of squares and turns it into a line of squares, this is me hiding some math from you. But for our purposes, just imagine that the AI is taking these numbers that represent the colors in the image, and it's randomly crumpling them. It doesn't do it with any idea. It doesn't know anything about cats and dogs or benign or malignant tumors. It compresses these numbers into a smaller set of numbers in a random way. It then takes that set of numbers and again randomly compresses them again until it ends up at the end with just 2 numbers, which are represented by these 2 boxes next to one another in my slide here. So you can think of this part as the brain of the AI. It's taking all this input from the outside world, from this image, and compressing them down in some random way, using some random math into just 2 numbers. And we are now going to, as humans, we're going to look at these 2 numbers, and we're going to interpret these 2 numbers as the AI's mouth or its voice. This is the AI telling us whether it thinks it sees a cat or a dog in the photograph. If the second number is larger than the first number, that's the AI telling us that it thinks it sees a dog. If the first number is bigger than the second number, that's the AI telling us that it thinks it sees a cat. There's 2 choices that it has here. Either the first number is bigger than the second number, or the other way around. So far, so good? Hopefully I haven't lost anybody yet. Okay, so again, it's just a computer program. We feed in a photograph, and at the other side, we get back 2 numbers. In my cartoon example here, imagine that because of this random compression, just by chance, the second number is larger. That's the AI telling us, I think I see a dog in this photograph. As we know, it's wrong in this case. The computer program or the AI has made a mistake. So what the AI does at this point is to run its run the computer program in reverse, which you can see by the change in direction of the arrows. We've told the computer it's made a mistake. It says it sees a dog. We tell it, no, this is a cat. You've made a mistake. At this point, the AI is going to uncompress those 2 numbers in the way that it compressed them. So just to offer a metaphor here, I don't know about you, but I know I've made lots of mistakes over the last week, tons of them. I can't quite remember everything I did wrong over the past week, and I definitely can't remember what I should have done to cause that error not to occur. plenty of situations over the past week where I said something I shouldn't have said, or vice versa, or done something that I should have done and so on. The good thing about computer programs is they don't forget anything. So again, we're going to skip over the math, but you'll have to trust me that the AI can take these two numbers plus the mistake it made and go backwards through this process. And everywhere that it made this random compression, it fixes that compression, or it alters the way it compresses those numbers, which I'm going to represent by the darker gray here. It's remembering that it made mistakes, and it can actually detect exactly where and when in the math it made a mistake, so that the next time we show it exactly the same picture, and now it compresses this picture again down into two numbers, the way it compresses those numbers has been altered a little bit so that it doesn't make the same mistake twice. In this case, it compresses the numbers in such a way that the first number is larger than the second number, which is the AI correctly telling us that it sees a cat rather than a dog. In a nutshell, that's basically how all the AI that runs on your phone and ChatGPT and X-ray analyzing AI, that's how it works. It takes in a whole bunch of input and figures out where it makes mistakes and improves itself so it doesn't make that mistake again. The magic of AI that everybody's now been exposed to over the last few years is that if you do this with not one image of a cat and one image of a dog, but a billion images of cats and a billion images of a dog, and you do this forward and backward trick over and over and over again, the AI is allowed to make billions and billions of mistakes, and every time it makes one of those mistakes, it alters the way it compresses the numbers in the image until eventually you can show it a new picture of a cat or a new picture of a tumor for which you do not know whether it's benign or malignant. And most of the time, the AI will now be able to successfully predict whether it's looking at a cat or whether it's actually looking at a malignant tumor that actually is malignant, or it knows that it's actually it predicts it's looking at a benign tumor when that tumor actually is benign. That's the AI revolution in a nutshell. Okay. As I'm sure you all know, there is now an exploding literature about ways of applying AI to clinical problems. Here's one I just kind of chose at random, but it shows you sort of the basic workflow here. So forget cats and dogs. We put someone in a scanner, an fMRI, and we get back a scan, which again is ultimately just an image, and that image is made up of a whole bunch of colorized pixels. And if we train the AI in the way that I just described, ultimately we can get an AI that becomes very, very good at being able to make predictions at the level of human experts, or in many areas now beyond the ability of human experts. It's able to see or understand patterns that are beyond human ability. It's a greatly unsettling fact for a lot of us specialists, but that's the state of play at the moment. So far, so good. If anybody wants any clarification, please speak up. I'm happy to go back over anything. Going once, going twice. Okay. Okay. That's sort of been this AI for the last 30 years. In the last 5 years, there's been some advances in AI that have led to things like ChatGPT and the ability for the general public to hop onto a website and ask questions to what seems like a medical expert and ask for medical advice and get back responses in plain English that look like sound medical advice, which may or may not be sound medical advice. This is this now uncomfortable phase that we're in with these what are known as large language models. And I'm going to talk a little bit about those now. So let's start where we left off. We have this computer program that takes as input an image and can correctly now compress all the colors in that image down into two numbers to predict whether it's seeing a cat or a dog. It turns out that this computer program, you can invert it in the following sense. You can treat these two numbers at the end of the computer program as keys on a keyboard. You can type numbers into these two boxes, like for example, putting a very large number in the first box, the green box here, and putting a very small number in the dog box. And if you then ask the AI to uncompress those two numbers that you've put in, it will start to hallucinate. There will be colors that arrive back at the level of the eye. And if you then render those colors, you will get basically what the AI thinks a cat is. This was something that was quite surprising to everyone that worked in AI about 10 years ago. This is the most cat-like image that this AI can imagine. What we're looking at now is often known as generative AI. We're not giving it a picture and asking it to make predictions about what's in the picture. We're doing the opposite. We're asking it about a concept like cat or dog, and it generates an image or an example of that concept. That's generative AI. This idea of generative AI, this is what all of ChatGPT and Llama and Stable Diffusion, all these things that you can talk to them or ask them to paint pretty pictures, that's what they're doing. Your prompt, the thing that you type in, is going in one side of the algorithm and causing the algorithm or the computer program to generate, in this case, an image. So imagine now we don't want to say cat or dog. We want to type in or prompt the AI. We want to ask arbitrary questions like this question: how are you? Imagine we take our two boxes in which we can put numbers and we extend it into 26 boxes. And again, imagine these boxes are like keys on a keyboard. We can we can press on these keys, or we can type numbers into these boxes. If we have 26 boxes, which correspond to the 26 letters of the alphabet, we can take the first letter in this prompt, which is an H, and we can put a 1 in the 1, 2, 3, 4, 5, 6, 7, 8th box. We put a 1 in the H box, or the 8th box, and we put a 0 in all the other boxes and push those 26 numbers into this network. We then take the second letter, which is an O. We put a 1 in the O box and we put zeros in all the other boxes, push that into the AI, and we keep going. We do that for W space R space U question mark. And because this is a generative AI, we can look to see what comes out the far end. And in this case, what comes out is not colors that make an image. What comes out is a random sequence of characters. This is not a very good ChatGPT. It's a random set of characters. But we're now going to do the same trick that I showed you a few minutes before. We're going to tell the AI that it made a mistake. The X and the Z and the H are wrong. We're going to propagate those errors back, or give back all those errors, and then make some changes, and then go forward again until we get what we want, which in this case is all of the letters in the question have moved left by one step, and we've lost the H, it falls off the other end. And we wanted the AI to tack on the right-hand side here, the thing that should have followed, the letter that should have followed the question, how are you? If I had taken a poll, which of the 26 characters is most likely to follow how are you? I would imagine most of you would say the most likely character that would have followed is the character I. If we keep going, we then take that correct answer and we feed it back in the other side. We can repeat this game. We can ask it to now say, what is the character that should follow how are you question mark I? And if we keep going, we can play this game, and eventually this thing will learn to say I am fine whenever somebody asks how are you? How does the AI know that what should have come after the question mark is an I and not a V or a Q? It knows because this AI has been given pretty much every written document that can be pulled off of the internet. It's seen a whole bunch of humans write things like, how are you? And those humans tend to follow writing how are you with the letter I. It just learns, it's basically learning to play a game. It learns to predict the next letter in a string of characters and words. Everyone in AI, myself included, never thought this was actually going to work. And OpenAI, the company, proved us all wrong by showing that if you just do this simple trick, this going backwards and forwards through this AI and asking it to make slight changes whenever it makes a mistake, by repeating that process over and over again with enough text written by humans, this AI starts to be able to talk back to humans in ways that seem reasonable most of the time. Okay, I'm going to leave off there because most people are sort of curious about how ChatGPT works and all the rest of it. The scary thing about ChatGPT, as pretty much everybody knows at the moment, is most of the times it says something that seems like the right thing and actually is the right thing, but every once in a while it says the wrong thing. And even more worryingly, what it says sounds like the right thing. And I would imagine for a lot of you folks on this call, it's particularly frightening when people are asking ChatGPT for medical advice. For the general public, it often gives back something that looks like reasonable, scientific, professional health advice that is not just wrong, but possibly the absolutely what you shouldn't do to rectify whatever your health problem is. Again, speaking on behalf of the general AI community, I will say that nobody has any real good idea about how to fix that problem once and for all. For better or for worse, we now live in a world where we have AIs that can talk as if they know what they're talking about, but every once in a while, they're wrong. Happy to discuss more about that in the Q&A session. Okay, I'm going to move on to my third and final part of my talk. This is this particular space of AI in which I work, in which we ask the AI to generate interventions. So I just showed you an AI that can generate text as a response to a question. What you're going to see now is generative AI that can generate an intervention for an intervention that will yield a positive health outcome. Okay, so again, let's go back to our cartoon example of an AI where we're feeding in images and we get our two numbers at the end. In the example that I've shown you here, we're feeding in images, which is a two-dimensional sheet. It's a two-dimensional thing. Imagine we now alter this AI so that the right-hand side here is a three-dimensional object. It's a whole bunch of cubes. And if we go to the left side of this AI, we can again put numbers into these empty boxes. And we can watch how this AI uncompresses those two numbers into a three-dimensional set of numbers. And again, I'm representing those numbers as colors. In this case, we've got gray, red, blue, and green. In my lab, what we often train AI to generate is not to generate images or to generate strings of text. We ask the AI to generate robots, to actually generate machines that do something useful. What I'm going to show you in a few minutes is how this AI can generate biological machines that may be able to work safely inside the human body. That's the intervention that I'm talking about. What my lab is interested in is developing AI that can generate robots that do useful clinical work inside the human body. Okay, so here we go. We have an AI that is just randomly generating a 3D collection of numbers. We are now going to go in and look at all of these numbers in this in this 3D collection of numbers. And we're going to treat the numbers not as colors, we're going to treat them as physical objects. All of the numbers that correspond to the gray boxes here, we're going to assume this is the AI telling us to remove that material. So you'll notice here that we're starting to remove the gray boxes, and we're just going to leave all the other numbers there. So as we remove all the gray boxes, we're actually left with a three-dimensional collection of numbers. And there are three different numbers in this picture: the blue number, the green number, and the red number. We're going to ask our computer program to treat those three different numbers, or those three different colors, as actual cubes that have certain material properties. So what the AI does at this point is to take those red, blue, and green cubes and put them inside a video game that's running inside the computer. So inside the computer, we've got this AI that can generate collections of numbers. And then we have a video game that's treating those numbers as physical objects. In this particular animation that you're seeing here, all of the red cubes and the green cubes are being treated by the physics engine as little cubes that increase and decrease in volume. Here's an example of us then taking what the AI dreamed up and building it as a physical robot. What you're looking at here is a soft robot. Each cube here is made up of soft rubber or silicone. The cube is hollow inside, and you'll notice these two air valves. And there's a grad student that's standing just off camera, and that grad student is pumping air into and removing air from these empty cubes. What we're looking at is an AI that has no understanding of robots or silicone or moving robots. It's just generated these cubes at random. So at this point, we tell the AI that this robot is doing a better or worse job at whatever we want it to do. And if the robot is doing a poor job at whatever we want the robot to do, the AI makes slight changes to how it generated this structure in the first place. It's the same game that we always play with AI. We tell the AI that it made a mistake, and it slightly alters the thing that it generates in response to that error. And what happens over time is this AI starts to learn how to generate better and better robots, robots that are better and better at doing whatever we want them to do. I'm throwing a lot of material at you, so I'll just pause for a moment. Can I clarify anything? For our purposes here today, the main takeaway is we have an AI that's just a computer program. We're telling it when it makes mistakes, or when it makes mistakes in the thing that it generates. If it generates a robot, the robot is not doing what we want that robot to do. And by allowing it to make more and more robots, the AI automatically gets better and better at making better and better robots for us. I would imagine most of you on the call are not really interested in robots, so let me move on. In this case, you're looking at a robot that's made of inorganic material, rubber and air and valves and so on. Wouldn't it be great if we could make a much, much smaller robot that might be able to move within the human body? But it probably wouldn't be a good idea to make very, very small robots that are going to move about within the human body if they're made from inorganic parts. As I'm sure all of you know, one of the things that the body hates above all else is small amounts of plastic, which unfortunately we now have inside our bodies. Small bits of metal, ceramics, not a good idea. So wouldn't it be great if we could make very, very small robots that are made from materials that the human body is going to be okay with and will accept and won't trigger an immune response? The best set of materials would probably be to try and build the robot from the human patient's own cells. So what you're looking at is a soft robot. What you're looking at in this video is a biological robot. This robot is about 1 millimeter in diameter. We're looking down through the microscope at this biological robot, and it's walking very slowly along the bottom of a petri dish that's filled with room temperature fresh water. So I'm now going to return to AI for a moment, but just wanted to sort of orient you as to where we're going. In my lab, we try to create AI that designs useful robots for us. In the last 5 years, I've teamed up with some biology colleagues in which we take the same AI, but now we ask it to design robots that are built from biological components rather than technological components. Okay. So here's one of them here. This is a photograph of what's known now in the popular press as xenobots, Xenobots, xenobots. They're called xenobots because they're not made from human cells. At the moment, they're made from frog cells. They're made specifically from the frog Xenopus laevis. This xenobot is made up of about 2,000 frog cells. And the cells that are stained green, these are frog epithelial cells, and the cells that are stained red in this image are myocardiac tissue taken from frog. So frog heart and frog skin cells. Just to give you a sense of scale here, here is that exact xenobot trapped under glass. It's about 1 millimeter across. Okay, so we reported the first successful AI-designed biological robot back in 2020. And at that time, my team here teamed up with the Levin Lab, Michael Levin at Tufts, and his microsurgeon, Doug Blackiston. Doug told us at the time that he could liberate frog skin cells and frog myocardiac cells from very, very early frog embryo. And Doug told us that under the microscope, he could then rearrange any arbitrary number of these skin and heart cells into new patterns. So from our perspective, what we then did is turned around and told the AI that it can generate collections of 2 types of Lego bricks. The blue bricks, which are biophysical models of frog skin cells, and the red-green boxes here, which are biophysical models of frog heart cells. And we set our AI to work on this. So what you're watching here, as I mentioned now a few times on this call, the AI doesn't know anything about frog. It doesn't know anything about frogs, doesn't know anything about frog skin cells or heart cells. The only thing the AI knows is that these blue cubes, which correspond to frog skin cells, are passive and soft. If you watch these 3 videos, you'll notice that the blue cubes are being passively pushed and pulled by the red-green cubes. So this is us describing to the AI what it can build from. The red-green voxels, these are the red-green cubes. These are, we told the AI, these are active cubes. These cubes will, on their own, get bigger in volume and get smaller in volume spontaneously. It's not a very fancy model of heart cells or heart tissue, but good enough for our purposes. So what the generative AI did is it generated 100 different random collections of the green cubes and the red-green cubes, and I'm showing you just 3 of those 100 initial guesses. You'll notice that the red-green cubes are all flashing red and green out of sync with one another. I'm not a clinician, but even I know that heart cells, when they're working well, they synchronize. They all increase in volume and decrease in volume together to cause the heart to act as a pump. when we started this project, we asked Doug Blackiston, our microsurgeon, we said, what happens if you take frog heart cells, extract them from early frog embryo, and put those frog heart cells back together in new patterns, the 3 patterns that you see here, for example. If those cells are arranged in a pattern that's very far from natural frog heart, will those cells naturally synchronize or not? And Doug's answer was, I don't know, nobody's really tried this before. So in the face of that uncertainty, we told the AI basically that. We said these red-green voxels, they get bigger and smaller spontaneously, but when you put them together, don't expect them to synchronize. We told the AI, assume the worst, assume that they won't synchronize. And you can see that visually in the images here. When the cube is red, it's getting smaller, and when the cube is green, it's getting bigger. So you can see these models of frog heart cells getting bigger and smaller and not synchronizing whatsoever. So we have an AI now that's generating ideas for how to combine frog skin and frog heart, but we haven't told the AI what a good arrangement is. It can generate ideas, but the AI has no way to know whether an idea is a good idea or a bad idea, because we haven't told the AI yet what we want these biological robots to do. So in this very first experiment, we did tell the AI what we want these robots to do, which is to walk along the bottom of the virtual Petri dish as quickly as possible. Sheila was just saying, please drop your questions in chat. Okay. So we have now told the AI what we want. We want a walking bot. And as you can see here in these initial 3 random guesses that the AI has made, none of them walk along the bottom of the virtual Petri dish at all. They're all doing terrible at what we want the bot to do. But if you squint very carefully, you might notice that the bottommost one moves a very small distance to the left, further than the upper two bots do. So even though these are terrible machines, they do very poorly, one of them does a little bit better than the other 2. So what the AI does at this point is delete its bad ideas. It knows that it made mistakes in the upper bot and the middle bot, and it knows that it did not make a mistake in the bottom bot, or at least it's doing a little bit better. So the way in which the AI generated this bottom bot, it generates another one, but when it does its trick of generating, the way in which it generates this new 4th bot, it makes a slight change to the way it generated the 3rd bot. So in essence, it's making a slightly modified copy of that bottom bot. There's a question from Riker R here about ChatGPT. I will come back to your question about ChatGPT in the Q&A. So we've got an AI now that knows that this 3rd one is still terrible, but it did a little bit better than the other 2. So the AI makes a 4th one, which you can think of as like an offspring of this 3rd one. It's a 4th bot which resembles its parent. It resembles the one in the bottom. It might have a little bit more heart tissue here or a little bit more skin over here. And again, the AI will continue. It will delete the robots that do a poorer job at whatever it is we want them to do. In this case, walk from left to right along the bottom of the Petri dish. And the AI will make randomly modified copies of the surviving bots. This particular type of AI is known as an evolutionary algorithm. It's basically a computer program that does a whole bunch of trial and error, generates a whole bunch of things, and deletes the ways in which it generates the poor things and makes slight changes to the way it generated the better things. And like in natural evolution, sorry, it seemed to lost my screen share there. Let me try that again. Everybody see my screen again? Okay. So like in biological evolution, it starts to make more and more slight variants of the things that are doing a better job. And this evolutionary algorithm, this evolutionary approach to AI, we run this for a few weeks on UVM's supercomputer. And back in 2019, the AI eventually generated this design. And you'll notice that this particular biological robot walks from left to right along the bottom of the virtual petri dish. It's a little difficult to see in this video, but you'll have to trust me. It's walking in a more or less straight line to the right, even though the motors or the heart tissue, which is acting like the motors or the driver in this robot, is unsynchronized. So the AI has figured out how to build a biological machine from unreliable parts. The parts do not synchronize. So just to sort of give you some intuition here, imagine I asked you to design a boat, and in that boat you can place an arbitrary number of human rowers, and you can place those rowers anywhere you want in the boat. They're all going to row, but they won't synchronize with one another. And you want the boat plus the rowers to go straight. It's a very, very difficult task. I've asked plenty of my engineering colleagues if they can figure this out. No one's been able to figure it out yet. So this is another example of where AI is exceeding what human specialists can do. It turns out that you can combine frog skin and frog heart tissue in a particular way to produce a small thing that walks along the bottom of a petri dish. The million-dollar question is, how do you put skin and heart together? None of my biology colleagues have been able to answer this either. Here's the AI saying, I think this will work. This is still a design that lives in the computer. We haven't tried this in reality yet. So it is the AI designing something and also, again, making a prediction, which is where we started our discussion this morning. The AI is basically telling us with this video, it says, put frog skin, which is the blue, put that on the dorsal surface, take some frog myocardiac tissue, which is the red-green stuff, put that on the ventral surface or the bottom part of this thing, and then put it in a petri dish, and I predict that that bot will walk along the bottom of the petri dish. Okay. So that's the prediction. So we took this actual video, which was generated by the AI. We emailed that video to our microsurgeon colleague, Doug Blackiston at Tufts. And he watched the video and then started to try and construct this bot under the microscope. It's a very long, drawn-out process. So I'll just show you a few highlights from this process. Again, we're looking down through the microscope with Doug. We're looking down into a small depression in the bottom of the petri dish. That's what the black circle is. At this point in the fabrication process, Doug has extracted about 2,000 cells from a early frog embryo. You can see the individual cells here. They're very adhesive at this stage in development. They bump into one another, and because they're adhesive or sticky, they start to glom together into a bit of a sheet. Doug looks at the video, deposits another layer of myocardiac tissue, puts down a little bit of heart, a little bit more heart, a little bit skin, a little bit heart, a little bit skin, basically building like a hero sandwich. He's trying to put down these two different cell types in the way that the AI said he should, which is put a whole bunch of myocardiac cells in the bottom and then layer some skin cells on top. I'm now showing you towards the end of this process. Doug is still looking through the microscope here, and he's working with microsurgical tools. So these are pliers and forceps that are about 1 millimeter across. And he's scraping away some of the unwanted material. So he's got the cells distributed in the way he wants. He's finishing this off by trying to get the 3D geometry of this little thing just right. So the high tech part is basically the AI side. The biology part here, this is, you know, like Michelangelo sculpted 400 years ago. Just put stuff here and then scrape away the stuff that you don't want. There isn't really anything fancy going on the biology side. You might notice in this video that he's kind of working on he's got the bot upside down. He's trying to get the shape of the legs just right. When he finishes with this sculpting process, he took the bot you just saw, which was upside down, turns it right side up, and that's what you're seeing in the video now. Thanks to the myocardiac tissue, which is on the bottom, you can't quite see it here. The myocardiac tissue is spontaneously pulsing and causing this little bot to walk along the bottom of a petri dish. Okay. Any questions specifically about that? I don't think so. Okay, so that's how we sort of combine AI, robotics, and synthetic biology here. We ask an AI to design a robot for us that's built from biological parts. How is this an intervention in health outcomes? It is not yet an intervention in health outcomes, but we're working on it. We took some of the bots that I just showed you and we put them together as a swarm and put them back in a petri dish. And then we distributed in that dish very small glass beads that are smaller than the bots. And it's hard to see in the bottom video. You can see it a little bit better in the simulation in the top. They sort of act like little robot vacuum cleaners or little Roombas. They manage to clean up some of these small glass particles. So you can imagine someday, hopefully, we can develop bots like this that are able to move through arteries and pull away at plaque, or scrape away unwanted material and bone growth, or are able to scrape away cancerous tumors. Basically something that pushes or pulls or cleans up small bits of stuff in the body that are unwanted. At the moment, that's still science fiction, but at least we have the beginnings of a technology that could work for that purpose. There's another branch of robotics known as intelligent drug delivery, where the idea was you would swallow a pill, which is not actually a pill, it's a robot. And inside that robot pill is a small amount of medication. And that small robot would operate like a sniffer dog inside the body. It would be able to detect proteins or macromolecules given off by a cancerous tumor and swim upstream towards the tumor, and when it reaches the tumor is able to deposit medication directly in situ at the site. Again, science fiction, but we're now able to ask the AI to design a bot that can wrap its body around a small bit of medication and go somewhere to deliver it. Last thing I wanted to say about this is what I've shown you here is xenobots, so bots that are made from frog cells. There is nothing about this process that's specific to frog. We are now in the process of generalizing this approach to what are somewhat tongue-in-cheek known as anthrobots, bots that are made from human cells. We have a preprint based on this, not a preprint, actually, sorry, it came out, it's already been published. I don't have time to go in the details, but if you're interested in this, you can go and read up on anthrobots at this citation. These are bots that are made from human cells. So these are, it's possible that we could make these bots from a human patient's own cells, and which would by definition avoid an immunological response, because these bots, if introduced into your body, are literally you. Okay, we got 10 minutes left. I want to make sure to leave time for questions. I covered a lot of ground, but hopefully I gave you a sense for what AI is, which is it's a lot of different things, and it's clearly being applied and going to be applied in all sorts of areas of the clinical sciences. Of course, I did none of this actual work. All the actual hard work was done by all the folks you see on the left, my current and former PhD students and postdocs, with the help of my collaborators on the right. And everything you saw was funded either by the National Science Foundation or the Department of Defense. We also got some financial support from UVM itself. Okay, thanks for your attention. I'm happy to chat. Okay.
Hey, everyone, if you can put your questions in the chat or put your intent to ask a question in the chat, because I don't see the hand raise function in Zoom anymore. So
You just have to click on the react heart and it will give you the option if you click on the heart.
okay.
So I see a question here from Riker R about consent form translation. Can ChatGPT or other AI do this reliably and cheaply and quickly? Absolutely yes to cheaply and absolutely yes to quickly. As to reliably, not 100%. Again, I don't know what the policy implications or the clinical implications are of that. Most of the time, if you've ever done any machine translation and you can go to a website and ask it to translate an English sentence into Spanish or French, and assuming you speak those languages, you can see how well or how poorly a job it does at that. One of the things that I find particularly worrying about ChatGPT and all of these human language-based AIs is that it often knows it made a mistake, but it doesn't know how bad that mistake is. So for example, if somebody signs a consent form saying, I do not agree to this surgical procedure, and when it's translated, the AI translates it into, I do give consent for that surgical procedure. From the AI's perspective, that mistake is no more problematic than it failing to capitalize one character in the translation. So the AI knows it made a mistake, but every human knows that the first mistake is much, much worse and much scarier than making a typo. So part of the problem here is that this is known as the alignment problem, is that AIs are not aligned with human values. Humans know certain mistakes are much more dangerous or immoral than other mistakes. And again, I would say, speaking from the AI community, nobody yet has in my opinion, nobody has a good idea about how to improve AI so that it knows these kinds of mistakes aren't such a big deal, like typos, but changing the word yes to no or vice versa in a consent form, that's absolutely, a huge no-no. It doesn't understand the moral magnitudes of the mistakes that it can make. If anybody has any idea how to solve that problem, I would love to hear from you.
Gary, if you want to ask your question.
Oh, yeah,
Yes.
Gary.
Josh, that was a really informative talk,
Great.
very, very much so. Can you comment a little bit about reliability, liability, and responsibility?
Oh boy, okay. Yeah, liability and responsibility. I'm speaking outside my area of professional expertise. I'm not a lawyer. I don't see any way that we can ever hold the AI, morally responsible for anything. So the AI is off the hook for liability and responsibility and morality. So who's to blame? It's easy to point at the coders or the company that hired the coders that coded up the AI. Again, I think that's an easy out. What I would say is that someone or the organization is deciding on the training data. What do we give to the AI in order to learn how to do what it does? I think that's the fulcrum. That's where we can apply legal and policy force. That companies in the near future are not going to be allowed to arbitrarily scrape the internet and just throw that at the AI and claim that was good enough for due diligence. I'm assuming in medical school, there's very careful oversight of syllabi and what we teach medical students for very good reason. That's a practitioner that goes on to make mistakes. You can look at their education. Did they get the proper training for what they were supposed to do? Again, not my area of expertise, but I think we can migrate a lot of the legal framework around things like that, about formal training. Engineers and clinicians are held to very careful standards in terms of formal training and education. Some of that can be adapted, not that relatively easily, to the ways in which we train AI. At the moment, there is no such regulation. It's the Wild West. So at the moment, I would say, yes, the companies are liable. They're responsible for the things that are going wrong at the moment.
So there's no consent form where you go ahead and you secure an AI program.
No, but I would say if company X deploys an autonomous car and it kills a kid in 15 years, and you work backwards from that event to the AI inside the car, and then what that AI saw previously. If in that data set it never saw children, that company is, in my opinion, criminally responsible. The company should have known that the AI should know something about the difference between children and adults when they're crossing the road. Again, it's not that far from what we do with humans. So I think there's hope for policy and regulation. It's going to take a while. We're just starting.
Okay, we have a question from Turner.
Josh, that was great. I loved it. But a technical question, and maybe there isn't an answer yet, but why are AI systems so breathtakingly inefficient? Our kid figured out a cat from a dog with 100 iterations, and AI is soaking up hundreds of billions of clock cycles and all of the electricity in Denmark in order to tell a cat from a dog.
Okay, that's a great question. So nothing against your offspring, but it's not just them, right? So you said your kid learned efficiently, but your kid is a result of you, and you survived long enough to produce them. You went through, a learning process, as did your parents, as did their parents. So if you think about, the thermodynamic and the computational capacity going back several billion years, each individual human and each individual organism obviously has inheriting the success of its parents by definition, because the parents survived long enough. So there is an evolutionary component to all this that we need to take into account when we think about these AIs. So you're right, an individual AI might take quite a bit of carbon to train, but that AI can generate another AI, and that AI requires less carbon itself to do as well or slightly better than its parental AI. So one of the things we need to do, again, as we think about regulation of the energetic costs of all of these things, is we need to remember it's not just about the individual AI. AIs can get more efficient at generating, can get better at generating more efficient and hopefully less erroneous descendant AIs, in the same way that it happened in nature. That's why your kid's so good at it, that they were set up thanks to all of their ancestors to approach the problem in the right way.
But what I'm arguing for, I think, is we just seem to be assuming that the backpropagation algorithm is the way it is. But there may be massively better ways to do it, which our kid tumbled to based on evolution.
Got it. Yeah, you absolutely right. I mean, I would say the evidence for backpropagation in the brain is scanty at best. It may be that the brain is doing something very different and more efficient. Maybe, or not. Maybe it is doing backprop, and it's just that the evolutionary constraints on, the nervous system and the brain and the visual system is set up so that backprop in the brain is very efficient.
Is there any way to determine how in the hell the brain is doing it?
That's beyond my area of expertise. I mean, what I've seen in the literature is people are making progress. They're pointing at things that look like backprop, but yeah, they definitely haven't ruled out that there aren't other things going on. But I don't see why it isn't something that we can, you can figure out scientifically in the years to come.
There's a lot of money to be made if somebody can figure out how to do it with less carbon.
Yeah, absolutely, there is. Absolutely. Great question. Thank you.
There's an additional question in the chat. I'm not sure how this would apply to bots, but do you have any thoughts on AIs facing each other?
Yeah, okay, so that's a great question. There is a whole field dedicated to this, and I didn't have time to talk about it. If you're interested, you can go to Google Scholar and type in antagonistic AIs. So it's exactly what you say. They just point them towards one another, and the reward for one of them is its ability to sniff out errors in the other. It's an interesting field. I think it's promising, but it doesn't get at the root problem of alignment. If one of the AIs doesn't know that kids cross roads differently than adults, there's no way that it's going to be able to identify a moral blind spot in the other one, right? If it still doesn't involve humans, how do you get that, what we call moral alignment in there? It helps, but it doesn't solve the fundamental problem of alignment yet.
Okay, I think we're reaching our time here. So I would like to thank everyone for joining. Next Friday, June 7th, our seminar series continues with a panel discussion on sustainability, health, and health equity in rural areas, needs and opportunities. Please join us at noon and check out our website for the link. Thank you.
Thanks, everyone.
Thank you,
I
Josh.
Really enjoyed the conversation. Thanks for your attention and your questions.
It was awesome.
Yeah, it was awesome, Josh. Thank you very much.
Bye-bye now.
Bye.